All right, welcome. And now we're going to start our unit on functions. So we're going to start with the section A, which is on the building blocks of mathematical models. So we're going to get into definitions of functions, what is a function, and we'll go from there. Okay, so a function describes how a dependent variable changes with respect to one or more independent variables. When there are only two variables, we often summarized as an ordered pair with an independent variable first. So this is where we get our x and y coordinates. Okay, so we have two variables. We have the dependent variable and the independent variable. And a function describes how the dependent variable is affected by the independent variable. And there could be more than one independent variable in a function. Okay, but we typically deal with two variables, one independent, one dependent. Okay, so again, we always list the independent variable first in an ordered pair. Notice the parentheses, right? So this would also be typically x, and then our dependent variable is usually we use y. Okay, so sometimes we'll see written as x comma y. Okay, and that's what we're saying here. Now, as a function, we use a different notation. If we do have a function, then we would write it in this form: y equals f of x, which really means, if we read it, it's a function of x. Okay, and that's the way we write y. Okay, so we might say that f of x is equal to 3x plus 4, right? So that would be the function where f of x just replaces y. All right, so now in this example, it says for each situation, express the given function words, write the two variables as an ordered pair, and then write the function in the notation of y equals f of x. So here we go. So A says you are riding in a hot air balloon. As the balloon rises, the surrounding atmospheric pressure decreases, causing your ears to pop. All right, so which is the independent variable and which is the dependent variable? So which controls what, right? So does the height of the balloon affect the atmospheric pressure, or does the atmospheric pressure affect the height of the balloon, right? So we're talking about altitude and air pressure, right? So which is the independent variable? In this case, it would be the right, so we got air pressure. So the independent variable is going to be what? In this case, what is dependent on what? The air pressure is dependent on the height of the balloon. So pressure is the dependent variable and altitude is the independent variable. So the ordered pair would look something like this. And so altitude would be your x and the atmospheric pressure would be your y. And so we would write it in function notation. We would say, okay, let A represent altitude and let P represent air pressure. And so we would say the air pressure is a function of altitude. P equals F of A. Okay, so we don't have to use X and Y as our variables, right? We can use any letter that we want to use that represents the quantity or the variable that we're measuring. All right, here we go. All right, B. You're on a barge headed south down the Mississippi River. You notice that the width of the river changes as you travel southward with the current. So you start at some point, right? right? And so you start at some point, and the further south you go, the wider the river seems to get. Okay, so we'll say at some starting point, right? You have to have some starting point. So the distance from that starting point, we'll say is D. Oops. Okay. And we'll use W as for the width of the river. So in this case here, which is the independent variable and which is the dependent variable? So I would say that the width of the river is dependent on the distance you are from the starting point, how far south you are from where you started. So that would be, so distance would be the independent variable. And width would be the dependent variable. And so we write the function. Here's the ordered pair, right? So we write it as an ordered pair. And in this case, they're going to use D as the to represent distance and W to represent the river width, right? So the independent variable is D and W. All right, and then of course we write the function as W equals a function of distance. W equals f of D. All right, now representing functions, there are three basic ways to represent a function. The first way is to use a table of values, right? An X and Y column table, where you can see how one variable changes as the other variable changes. You can draw a picture or a graph, or you can write an equation or formula. And that's what we call graphical. You have the table, graphical display, or you can use write it algebraically. All right, so now let's talk about domain and range. The domain of a function is the set of all values of the independent variable that both make sense and are of interest for the function. So these are all of the values of the independent variable that will go into the function or can go into the function. And again, there depends on the situation and what you're looking at. The range of the function is all of the values that come out of the function as the dependent variable, okay? And these values also correspond to the values in the domain. They're dependent on the values in the domain, of course, from the independent variable. Excuse me. So the range are all the values that come out of the function, that are able to come out of the function based on the domain of the function, okay? So when we create and using graphs of functions, so here are the steps that we go by. First, we have to identify the independent and dependent variables of the function. And then the second thing is identify the domain and range of the function. And then we're going to use the information to choose the scale and labels on the axes, and then zoom in on the region of interest to make the graph easier to read. And we're talking about a graphing calculator when we talk about zooming in, okay? So on a graphing calculator, we want to make sure we have the correct window. And in order to have the correct window, we have to either read the problem carefully and make sure that they tell us, if they tell us any information about what they want us to graph, or we have to know the range and the domain of the function to help give us an idea of how to set the window up. 3, make the graph using the given data. If appropriate, fill in the gaps between data points. And 4, Before accepting any predictions of the model, be sure to evaluate the data and assumptions from which the model was built. Make sure that they are still acceptable and reasonable. So now let's look at this example here, hours of daylight as a function. The number of hours of daylight varies with the seasons. Use the following data for 40 degrees north latitude to model the change in the number of daylight hours with time. So first, the number of hours of daylight is greatest on the summer solstice around June 21st, when there are about 14 hours of daylight. The number of hours of daylight is smallest during the winter solstice around December 21st, when there are about 10 hours of daylight. And then we have the two equinoxes. So we've got the spring and fall equinoxes, and those are about around March 21st and September 21st, respectively. There are about 12 hours of daylight, so about the same number of daylight hours as there are nighttime hours. Okay, so now we've got 4 points that we can plot throughout the year. Okay, now also consider that time is the independent variable. In fact, time passes regardless of any other event. And so time, whenever time is involved, we always use time as the independent variable, and we typically use t to denote time. We also let the hours of daylight denoted by h be the dependent variable, okay, because that's, again, dependent on the time of year that we're talking about. So h is going to be the number of hours of daylight. And then so we're going to write the function h equals a function of t. Now, the domain is all times, but we're going to say 3 years. We're going to use a 3-year period as a time of interest. And of course, the range goes from 10, the minimum amount of daylight hours, 10 to 14 hours of daylight. And of course, the number of hours of daylight changes smoothly with the seasons. So it's not going to be a discrete change in the number of days hours. It's a nice continuous curve. And also, this pattern repeats itself every single year. And this is called a periodic function or a cyclic function. And so here's what it looks like. So you can map the first 12 months, right? The first 365 days. So you can map out the first 4, right? You've got the spring equinox, summer solstice, fall equinox, and winter solstice, and then it repeats itself. And so once you get the first cycle done, so start at the minimum, right? Minimum of 10, peaks at 14, and then it goes right back to 10. And so once you have the first 365 days mapped, then you can see that it just repeats itself. All right. Okay, that's it. You have a great day.